in fact, we want to discuss the importance of feature engineering for, reading time on a clock, for example. What is the difference between deep learning, multi-layer perceptron, and the perceptron, for example? So, for example, if you have an image, if my raw data is, or if we need to build a model, in fact, for predicting time, for example, we need to build a model to predict time, or we need to build a model where we can feed it with images of a clock, and it should be able to predict time, for example. So if you are working with convolutional neural network, if you are working with deep learning, you can just feed it with the raw data, with the images. Because as I told you, in deep learning, we don't care about normalization and the standardization and all those things, because if we did it, it's fine. But if you didn't, it will be also okay. We just need more data, in fact, to train our model. In deep learning, it's complex model, and it has lots of weights which we need to adjust, for example. And to do this, we need huge data set. We need to work with a big data set, in fact. So if you are working with convolutional neural network, you just feed it with the images, with the raw data. It's pixel grid, for example. So it will be able to, but we need to train it with a big data set. If you are working with multi-layer perceptron, so it's smart to try to simplify it. How can we do this? We can do this by try to get some features from the image. So I have this image, for example. So instead of working with using the image, of course I can use the image similar to what we did with MNIST dataset. But maybe if you are working with MLP, it would be smart to simplify it and just to try to, for example, to send the XY coordinates of each handle. So I need to send this point, and I need to send the coordinate of this point. So each is, this point, it will have, if I put this one in XY coordinates, for example, so maybe for this clock handle, this one, it will be X1 and Y1. And for the other one, for our handle, it will be X2 and Y2. So if you are working with multi-layer perceptron, it's smart to try to work with feature extraction and try to provide some features to the MLB to be simple, and at the same time to be able to train it. So maybe for MLB, we need to send the coordinates, XY coordinates of the clock handles. If you are working with a perceptron, the perceptron is a very simple model, and then maybe we can just send, this angle, θ1 and θ2, for example. So if you have this one, I can just send, this angle, θ1 and θ2. So it will be more simple. So in case of perceptron, here we will have two inputs, right? In case of MLB, we will have 4 inputs. It will be more complex, correct? Maybe for CNN, we don't care. We can just send pixel-wise or pixel grid. We can just send a pixel grid. See, so if this image, it's 28 times 28, similar to MNIST. So total number of inputs will be 784. So if you are working with deep learning, there is no problem at all. You can just feed it with the raw data. If you are working with MLB, you need to work a little bit and try to extract some features from the image and feed the model with those features. If you are working with a perceptron, maybe you need to go deeply into your data and try to make it simple for the model. So at the end, we have a model. We will provide it with the data, for example, or feature engineered data, for example, and we will try to approximate time, for example, or predict time. So in deep learning, do we still need feature engineering? In fact, we don't need it. We don't need it, but if you can do it, you will make life much easier for your model. But in reality, deep learning, it's meant for working with raw data, because when you look around, we have lots of raw data around us, and it's impossible for us, in fact, to label those data or try to feature engineering those data. But if you can do it, you will make life much easier for your model. Overfitting and underfitting. Underfitting, we have been discussing those before. Overfitting, it refers, overfitting, it's just memorizing, the model is just memorizing the data. And to overcome, we just, we train we need to add some constraint on what information it's allowed to store, for example. So overfitting, we have overfitting and underfitting. Generalization, it's very important, and it refers to how well the trained model perform on data that it has never seen before. So I mean, in machine learning, we divide the data into one for training, one set for training, one set for testing, for example. So the one for testing, we call it hold out. We keep it away for testing the system. And it's important because from the accuracy of training and the accuracy of testing, we can decide if the system can generalize, in fact. Overfitting, where the model just memorizing the data, and to overcome this, we need to maybe train the model with more data or add some constraint on what information is allowed to store. It is allowed to store. A model trained on more data will naturally generalize better. So we need more data, in fact, because I mean, overfitting means the model has higher capacity. Higher capacity means the model is very powerful, in fact. So the model has more weights. So if you have a model with 3 parameters, like a perceptron, it's different from a model which has 81 parameters, similar to what we had, what we did today, for example. So when it has 81 parameters, it has more capacity, in fact. So chances to memorize the data set will be very high, will be much higher. So in this case, we need to stop the model, maybe from because if you keep training the model, I mean, the idea here, you have a small data set and the model has higher capacity, and if you will keep training the model, at some point the model will just memorize the data, right? So to avoid this, you can just stop the model from training, or you can extend your data set. We need to expand the data set. So if you are working with images, you can use some techniques from image processing to expand your data set, right? Maybe adding some noise to the image, maybe rotate the image, correct? So you can use a set of image to generate or double the size of your data set. In this case, the model will have better chances to train without going into overfitting. We also can put some restrictions on the weights. So we don't allow weights to just take any value. We can put some restrictions on those weights. So generalization is very important, and we can identify if the model is overfitting from the performance in the training and the performance in the testing. Underfitting, it's simple, because underfitting, it means the model is too simple to my data. So if you are, for example, working, if you are using a perceptron for multi-classification for MNIST data set, of course, it will underfit your data. I mean, the accuracy will be very low because the model is very, very simple. We need to have more complex model. Some techniques to overcome overfitting. It's regularization technique, for example. We can add L1 and L2 regularization techniques, for example, and in this way we have this cost function, which we try to minimize. We try to minimize the difference between. We try to minimize the square root of the error. I mean, this error, it's the difference between the target value and the predicted value. T, it's the target, and O, it's the predicted. So if we can add the part here, so instead of minimizing only the error, we will minimize the summation of squared weights. So in this case, we will try to minimize weights. We will not allow weights to take any value. In fact, we try to minimize it as well. So we try to minimize this error, and at the same time, also we need to force the optimizer to minimize the total sum of your weights. So in this case, we try to we try to reduce the model capacity, in fact, because if you will allow weights to take any values, at some point some of those weights will just take very large values, and then when it's large, it will give more weight, in fact, to some. So imagine that I have this input here, and the weight value which is connected to this value will get too much. It will become very, very high. So in this case, we will give more weight to this specific input, and we will ignore the rest. So this one will be used for decision making, and the rest will be ignored. So imagine you are going to the bank for applying for a loan, for example, and you provide income, you provide age, years of experience, and so on, and they just focus on age. So young people will have better priority of better chances for getting loan, for example, regardless of income, regardless of years of experience, and so on. So in this case, in fact, the model will try to, it will be selective. It will try to do some feature selection by itself. So using this regularization technique here, we will try to force the model to reduce the total sum of weights. So all weights will have, will not get too high, for example. So this is one technique called L1 and L2 regularization techniques. And also we can add something called the dropout. Dropout also, it's one way for reducing the model capacity. And in dropout, we just drop out some nodes. So for example, you have a hidden layer, and this hidden layer, for example, has 4 nodes, for example. If you selected the dropout coefficient equal 0.5, it means we will drop 50% of those nodes. Dropout means when we go forward, we will use those weights. I mean, it will be just normal when we go forward for calculating the outputs. And then when we calculate the outputs, we will calculate the error, and we will go backward for adjusting those weights. When we go backward, we will drop 50% of those weights. And then when we drop a node, for example, all weights which are connected to it will not be adjusted. So all weights which are connected to this dropped out nodes, it will not be adjusted in the forward, in the backward phase, for example. So when we go backward for adjusting weights, we will not adjust the weights which are connected to those dropped out nodes. So in this case, we will adjust some weights, and some other weights we will not touch it, right? So it's like updating only 50% of the weights. So in this case, we can say, okay, we will adjust some weights, the rest will stay as it is, for example. So not all weights will be increased. So we have dropout, we have regularization techniques, L1 and L2 techniques, and of course, we try, in gradient descent, for example, we try to find delta omega, right? Delta omega, it's minus eta multiplied by partial E by partial omega. So we calculate delta omega, which is minus eta multiplied partial E by partial omega. This one, it's the learning rate, and this one, it's a cost function, which we try to minimize. So this cost function, it's a mean squared error, so we can just add that part to it, right? So when we differentiate, we will try to minimize this summation effect, right? We try to minimize to calculate delta omega. So delta omega will include that part here. Yes. So there are many ways, in fact, for those size reduction, for example. If you can, the simplest way to prevent overfitting is to reduce the size of your model. So the number of learnable parameters in the model, which is determined by the number of layers and number of units per layer. So those, size reduction, it's just, we try to work with a simple model as much as possible, right? So when we use the perceptron for, today for this XOR problem, and we used a perceptron, and then the second time we used a multi-layer perceptron. One time we used the 3 units, and sometimes we used the 81 weights. So this is a size reduction. When we talk about size reduction, try to simplify it. Try to use a simpler model. So in deep learning, the number of learnable parameters is often referred to as the model capacity. A model with more parameters has more memorization capacity, in fact, and therefore can easily learn a perfect dictionary, like a mapping between training samples and their targets. So when your model is really very complex, when your model has higher capacity, has higher trainable parameters, it will be more capable for memorizing the data set instead of learning it. So there is no magical formula for determining the right number of layers. There is no rule for selecting how many hidden layers, how many units per hidden layer. It's just by trial and error. But as we mentioned, we should start with a simple one and try to make it complex with time. So at the beginning, it's better to have underfitting, and after that, increase complexity of your model until you have good solution. So general workflow is to find appropriate model. Size is to start with relatively few layers and parameters, and increase the size of the layers or add new layers until you see more reduction in validation loss. So start with a simple one, and after that, you can just increase number of hidden layers, you increase number of units in each hidden layer until you have good performance. In this graph, for example, I have this original model. I have this model. This is the response of a model. And if you want this is the original model. And if you simplify the model, you make it more simple. For example, you reduce the number of hidden layers or number of units per hidden layer, you will get this kind of response. In fact, this is the loss. So this is the loss which we need to minimize. We need to minimize this one. So this is the original model, and when you simplify it, you will get better results. I mean, the loss has been decreased, in fact, for the simple one. So it does not mean that when you have a complex model, it doesn't mean that you will get better results. So here also, this is the original model, big blue circles. And when you make it much bigger, in fact, you will get much bad response, much worse response. So you have, because it will overfit, in fact, this one will overfit. So when it overfit, you will get, no, sorry, this is the original model, and this is the bigger model. When the model is much bigger, I mean the error will increase. So it will overfit. It will overfit your data. Adding L1 and L2 regularization techniques, it will be like this one. So we have L1 and L2. So this one, it's L1, and this one, it's L2. We add the summation of, I mean, we add to the cost function. We try to minimize this one. Lambda multiplied by summation of absolute values of weights, or lambda multiplied by the summation of squared weights. So this one, it's L1, and this one, it's L2. You can try this one. I mean, next week, we will be studying error backpropagation, and I made an example, and I implemented it, in fact, for a feed-forward neural network with one hidden layer. You can add L1 and L2 to this cost function. And in my example, which we will use next week, I try to minimize mean squared error. So it's a summation of t minus y squared. So I try to minimize this one. If you want to add L1 and L2, you can just do it, right? You can just add. So because if you will use L2, for example, you just need to add here half summation of omega squared, correct? So when we can test what is the difference. So for example, for L2, this is the original model without regularization I mean technique, and then when you add L2, you will get better response like this one. So L1 and L2, they are very important. Adding a dropout also, as I mentioned, it's simple. So we need also to have a dropout coefficient. It could be, for example, 0.5. When it's 0.5 for this layer, for example, it means we need to drop out 50% of the nodes in the training phase. And each time it will be by random, for example. So each, for example, if you will be working with batch gradient. So in batch gradient, we calculate all the gradients for all data points. We will get the mean gradient, and we will adjust the weights each epoch only one time. So when we go back, we will drop out some of the nodes, and we will not adjust the weights which are connected to those nodes. So it should be possible also to add dropout to the example which I did. I will present next week, and you can test dropout. I mean, feature selection. Today, I have been talking about select k-best. So for feature selection, because feature selection, I have, I mean, the importance of feature selection can best be recognized when you are dealing with a data set that contains a huge number of features. I mean, you have a problem where you have, for example, 20 features or 100 features. So this type of data set is often referred to as high dimensional data set. When it's a high dimensional data set, which means we have lots of features, the increased the training and the complicated model, which in turn may lead to overfitting. I mean, with this high dimensionality, we have lots of problems. Increased the training and the complicated model, which in turn may lead to overfitting. The chances to overfit will be very high, because when you have 20 inputs, right? And when you have this hidden layer, if you have in this hidden layer, for example, 20 nodes, if you have 2 features, it will be 2 times 20. So I will have 40 weights. But if you have 10, it will be 10 times 20, which will be 200. So the model will be more complex. So when we simplify the model, when we try to reduce the set of features or the dimension of feature set, we will simplify the model. And when we simplify it, it will be just easy to train it, and we will avoid lots of complications such as overfitting, for example. So in higher dimensional feature set, there might be several features which are redundant. Sometimes we have redundant. So for example, if you are working in a system and you measure temperature by one sensor, and you are measure, for example, humidity by another sensor, for example, maybe both of them, there is a kind of redundancy between those two features. For example, if you working with this banking problem, you have age and years of experience. Maybe both are correlated, for example. So maybe one of them will be enough. So meaning these features are nothing but extensions of other essential features. These redundant features don't effectively contribute to the model training, and therefore there is a need to extract the most important and the most relevant features for a data set in order to get the most effective predictive modeling performance. So if you have 10 features, we need to select the most important, maybe 5, for example, and use those, reduce the set for training your model. So feature selection, it enables the machine learning algorithm to train faster. It will train faster. It reduces complexity of the model and it makes it easier to interpret. So this is what I said, what I called it's explainable, for example, AI. We need to build, I mean, if you can solve your problem with a perceptron, why should you use feed-forward or multi-layer perceptron, right? So when it's assembled, it will be easy to explain it, explainable AI. So we call this one, it's explainable AI. So when it's assembled, it will be easy to understand, it will be easy to explain it. It improves the accuracy of the model if the right subset is chosen, and it reduces overfitting. So when we try to select the most important features, I mean, it will be much better. So now we will talk about select k-best, and it's a univariate feature selection based on a statistical test. This one, in fact, it's based on chi-square score, for example. And it removes all the k highest scoring features or select the best k features, right? So for example, you have a problem. For example, if you can remember, we have been working with Iris dataset. And in Iris dataset, we have 4 features. We have X1, X2, X3, and X4. It's beta length and width, sepal length and width. So we have 4 features. And I remember I did this example one time using X1 and X2, one time using X1 and X3, correct? In fact, when I choose to because I need to visualize it. I need to plot it in 2-dimensional space. So I selected 2. I need to select 2, but I don't know how can I select 2, in fact. So I did that by random effects. So one time I picked the X1 and the X2, sometimes I picked X1 and X3, and I just did it. But in fact, this is not correct. If you want to do it correctly, you need to select, if you want to choose 2, you need to select the most powerful 2 features from those 4 features, right? How can we do this? Using statistics, because the statistics can find the correlation coefficient between inputs and output, for example. So I can find the most relevant features, the most important features, the most powerful features. We can use this select k-best, for example, and this one we can import it from sklearn feature selection. So we have something called feature selection in sklearn. One tool is select k-best. So we can use this one. And this one we need also to use chi-square statistical score. I did that, in fact, with Iris, because I mean, as I told you last time, when I solved Iris, if you can go back to the slides, you can see that sometimes, I mean, in one example, I used the X1 and the X2. In another example, I used the X1 and the X3. And I remember in another example, I used the X3 and the X4. In fact, I did that by myself in random. In fact, I didn't do it, I mean, based on any numbers or any calculations. But this is not the correct way for doing it. If you want to do it correctly, really, and if you want to simplify your data, you need to use a tool to help you to select the most powerful features from your set of features. So here I use the select k-best. And in select k-best, in fact, I defined it here, a selector called select k-best, and I use the chi-square. I mean, if you will search this one, you will find that you can use Fisher, for example, score. You can use the chi-square, for example. You can use the many other things. So here in this example, I'm using chi-square, and I send it x and y because it will find the chi-square correlation, something between x and y, and it will return x in u. X in u, it will be the reduced set, in fact. X in u, it will be the reduced set. So I did that here, in fact, and I can print the scores, which we will get. And from those scores, I can select also, this is all the scores, in fact. So I will get all the scores. And from all the scores, I can, scores of the selected features of top scores, because I want to select features of the top scores. I want to select the most powerful features. So when I did that, in fact, I got those numbers. Those are the scores. Do you see? For x1, we have this coefficient. For x2, we have this number 3.7. For the third one, it's 116. For x4, it's 67.04. So from your point of view, which one, if I need to select two, the most powerful two, which two should we select? I mean, from those scores, it's obvious that we should select this one and this one. I should select x3 and x4. x3 and x4, they are the most powerful features. They are more powerful, in fact. Right? So those are the most powerful features in my feature set. So if I want to reduce the feature set from 4 to 2, I mean, it's smart to select x3 and x4, not any other option, in fact. And if I want to sort them, I can select x3. If I want to select the best 3, for example, it should be x3, x4, and x1, because the score of x1 is 10.8. So, so in this case, it's sepal length, sepal width, petal length, and petal width. I need to select petal length and petal width for solving this problem. It will be more powerful. So if you will train a model for iris classification using x3 and x4, you should get better results, because I just provided the right feature to my model. Right? I just selected the most important. For example, if we can apply this example to MNIST. Okay, I will go to MNIST later on, but we need to first to continue with, no, I have BCA. So for example, if it is select best, can we apply this one to image? So can we apply select k-best approach to images? Yes, we can. Because if we can talk about MNIST dataset, for example, I have an image here. So all people are writing in the middle. Do you see? Most of the people are writing here in the middle, correct? I have lots of white spaces or white pixels. Those white pixels does not have any information for me, right? Especially those pixels who are close to the edges. They are not important for me at all. The most important is the part in the middle. So if I want to use select k-best, in fact, it should return me, I mean, the most influential pixels which are in the middle, because those pixels are the most important pixels in my handwritten digits, because all people are just writing in the middle, correct? I don't care about white pixels in the image, because if you look into that part, this part does not have any information for me, right? This part does not have any information for us. This almost in all images, correct? So this part is not important, correct? This part is not important in all images. So maybe the most important part in the image, it's the part in the middle. So not all pixels have the same importance. So I want you, in fact, to try to apply select k-best to MNIST dataset. You will get a score. I mean, you will get a vector. I mean, the size of this vector, it will be 1 times 874. And you can just select the model to give you the most important 10 pixels, 100 pixels, for example, or if you want, I mean, this 128 times 28. So if we need to plot it in, for example, 14 times 14, we just reduce it by 50%. So we need to plot something. You can select the most important 14 times 14 pixels and try to plot it. Yes, so we will take 10 minutes break now. You will apply you will apply this select k-best to MNIST dataset and try to select the most important 14 times 14 pixels and plot it. So we will stop here for 10 minutes. In those 10 minutes, please go back to this example. I used here select k-best with iris dataset. You just need to repeat this one with MNIST dataset. In MNIST dataset, we have 28 times 28 features. Please try to reduce it to 50%. For example, 14 times 14 or 10 times 10. If it will be 10 times 10, it means we need to select the most important 100 pixels. And you need to reshape it and plot it. And we need to see, is there any difference? Is there any connection? Is there any? Because if I will select the most important from each picture and I will reconstruct the image, I need to reconstruct it one more time using those 100 pixels. We need to see, does it still 3? 3 is still 3, 2 still 2, 1 still 1, or it's something different. So please, we will take a break now for 10 minutes, and you need to go to this example, and you need to apply the select k-best to MNIST dataset and try to reshape and plot it. So we need to get something. I got this one, in fact, from BCA. I used the principal component analysis. This is the original image, and I used the BCA for reconstructing those images again using a reduced set, using 144 principal component, in fact. 144, it means 12 times 12, correct? So try to do the same using select k-best. Select the k-best, select the most important 144 features and reconstruct the image and plot it one more time. And we will meet again after 10 minutes. Thank you very much.